Okay, yesterday we have discussed about the potential for various objects, for dipole, first for point particle, dipole, disk, yeah, and solid disk, sphere also, yeah, I think sphere also. It's very large disk. Okay. Oh yeah, sphere, yeah. What about sphere? Oh, this is the rod, yeah. Uniform charge rod. Okay, so we get the potential like this. Okay, I forgot to mention we have also to discuss thin sphere with radius R, capital R. Okay, so we have sphere. Okay, the radius is capital R here. Okay, we have two regions. This is first region, this is second region. The second region is for R greater or equal to capital R, okay? So from Gauss equation, you get that E2 at the region 2 is Q over 4 pi epsilon R. Okay, from Gauss equation, Gauss law, using Gauss law. You can read it the I think last week lecture about Gauss law. Okay, so the potential in this case is integral minus E2 dr. So the low boundary, the lower boundary, it's from plus infinity to a point, let's say the distance R, okay? And this is equals to minus plus infinity to R Q, sorry, the R squared, sorry, Q over 4 pi epsilon 0 R squared. So this will be Q over 4 pi epsilon 0 R plus 2R, plus infinity to R, okay? So this one should be Q over 4 pi epsilon R, okay? And for the first region, this R less than capital R, this VR, so this integral minus plus to a point inside the sphere, okay? So we have to split the region. For example, this plus infinity to capital R, this to the R minus integral R to R E1 dr. Okay. So you see that from Gauss equation, not from Gauss equation, Gauss law, okay? I have mentioned that for thin sphere, only the shell, the shell of the sphere without content, without it's not solid, thin sphere. You know, understand what I mean. So it should be that for E1 is equal to 0. Okay, so this is 0. So we'll have with this one. Okay, so this is Q over 4 pi epsilon capital R. Okay, so inside the sphere, inside the thin sphere, the shell, yes, the cell sphere. So this the field, the electric field is 0, but the potential is constant, and the magnitude is equal to this one. Okay. Any question? Any question?
No, sir, it's clear.
No question. Okay. 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 So homework you will be collected next Monday. So today you have already collected homework for module 1, number 6 until 10. This noon, at 12 o'clock. Okay. Any question? No. I will continue the material. Okay. Okay. Okay, we discuss about new material called capacitor. Oh, sorry, not before that, before the capacitor. Okay, before the capacitor, we have to discuss about electric properties. So we have, if we consider a matter or material according to electric properties, it is divided by, well, so far what we have discussed 2, there are so many, I think 4, 4 or 5. So we have, so in this lecture, at your level, in elementary physics, in this lecture, you will only consider insulator, let's say not insulator, conductors, insulator. So conductor means that this property, this material, could propagate something like that. I mean, the current, the electric current, well, it's a conductor, it's, it is good for propagate electric current. Electric current. And it is bad for propagating electric current. Okay, we will discuss it later, but in for the direct current, yeah, we'll discuss it more precise for indirect in the section of direct current. So this conductor, for example, if we charge a conductor, for example, we have let's say a metal, mostly conductor. And let's say, yeah, mostly conductor. So, for example, if we consider a solid sphere metal. So if we charge, given this sphere charge Q, then this charge will distribute let's say uniformly to the surface. Okay, let's say this is plus, so this charge will be distributed to the surface of the sphere. Yeah. Charge Q distribute only at surface. Okay, so it's similar to the thin sphere case. It means that the electric field in this inside the sphere, this metal sphere, is zero, but the electric field in the second region is equal to Q over 4 pi epsilon 0 r squared. Okay, you could derive it this E1 equal to 0 and E2 equal to Q over 4 pi epsilon 0 r squared using Gauss law. Yeah, okay, use Gauss law as your exercise. Okay, but if the sphere, for example, an insulator solid sphere, okay, if we charge Q here, okay, insulator solid sphere, so the final state, the final situation, this charge will be distributed, let's say, uniformly on the sphere, including the interior of the sphere. Okay, so this should be sigma over Q over 4 P squared P r squared. Okay, so this one is rho Q over 4 pi over 3 r to the, capital R to 3. Okay, So, well, I will discuss it later. So it should be the induced charge neglected. So usually if we charge the insulator sphere or insulator material, there will be induced charges, okay, in reality. But in this case, we neglected, okay. So only free charge here, only free charge dominate, okay. Free charges dominate. So let's say this neglected, okay. That's the properties of this electric material, conductors and insulator in the context of electrostatic. Is there any question? Any question? Okay, no question. Okay. No question. Do you understand what I talk about? All of you. All of you understand what I'm talking about? Hello, hello. Celine, can you
Yes,
tell
sir.
Arkan Usman ya to change his slide atau neglected? Okay, omitted. Okay.
What, sir?
Sorry, omitted, neglected. Arkan is late.
Oh, actually, he got into the waiting room when pas nama dia belum diganti, Pak. Then I told him to.
Yeah, okay. Tell him to change his name. Put his student ID first.
Okay.
Okay, back to the material lectures. I mean, do you understand what I'm talking about? Okay, good. Then we go to new section, new chapters. Capacitor. Do you know the definition of capacitor? The definition of capacitor.
A device that stores electrical energy, sir.
Yeah.
Usually found in circuits.
Yeah, it's an electric device. Yeah. Oh, I cannot. Okay. Just a moment. Okay, electric device. Stores. So an electric device that stores charge. Okay. So stores, the key point is stores. Sorry about that. Sorry, I should restart my Microsoft Whiteboard. Okay, what I have written, I have wrote missing. Ah, this one, okay. An error here. Ah, okay, the keywords here is stores. Yeah. So the capacitor is a device, but there is a properties called capacitance.
Sorry to interrupt, sir, but I think you haven't shared your screen yet.
Oh, oh, okay, sorry. Okay. Yeah, sorry. So capacitance is the ability let's say, what is the degree, how much degree or ability of capacitor to store charges. Okay. So the definition of this capacitance is C, we call C Q over delta V. Okay, it's delta V is the voltage difference. Voltage difference. Okay, Q is charge. Okay, let's begin to the simplest case. Plate or plate. Example. 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 Let's say a plate. Very large plate or rectangular. Okay, we have so usually this we have rectangular here where we omit the width of this rectangular. Well, let's say this one, it has a width here. Okay. So let's say this is the width. Let's say this is W width, yeah, and then they have length also L. Okay, so let's say this this plate, yeah, made from metal. This metal plate conductor, metal plate. Okay, if we charge it, then it will distribute to the surface. Okay. because this is very large, okay? And E here is equal to epsilon, sigma over 2 epsilon 0. Okay? Using Gauss law, again using Gauss law. What if we said like this? We have this, let's say, first plate. This is plus, for example, and this is the second plate. This is the second plate. Okay, this is minus sigma. So the distance between them, the distance between them, let's say D, okay? D is very small than the length, okay? Distance. What about, let's say this 1, 2, 3. E1 here equals to E2 here equals to E3 here equals to, Muhammad Aryatsya.
Yes, sir.
Muhammad, yeah. What is E1 here? E1. Riandito.
E1.
Yes. E1 is equals to Reno. Okay. Nobody's. Bagas Irfan.
I'm not sure, sir.
I'm not sure. Always unsure. Rafa.
I'm also unsure, sir.
Unsure, okay. So,
Sir?
okay. Since you are some of you unsure, maybe all of you unsure.
Sir?
So, yes?
Is E1 0?
Yeah, E1 is 0.
Okay.
But you know why? Why this is 0?
Because what's it called? The charges are going from positive to negative, so there's no charges going on the left side, I think.
Left side or right side? So this the left hand side charges will move to the other side, to the right, okay? Because there is a negative charge here. So there will be summed, collected. The charges will collect or summed in on the inner surface. This one also. So E2 here E2 here is equal to sigma over epsilon 0. There is no factor 1/2, okay? Is there any question about this?
Sir,
Yes.
why isn't there half on E2?
There is no half.
Yes, why?
Yeah. Okay. Use Gauss law. So in this case, the Gauss law we have. Sorry, not the blue one. Maybe. Let's say the red one or green one. So this is the Gauss law. This is the Gauss law. Sorry, the Gauss surface. Sorry. So this Gauss surface, if we thought this surface, this one, this E here is 2A, 2EA, 2EA equals to the Q enclosed over epsilon 0. So this Q enclosed here is sigma times A over epsilon 0. So we get this one. But in this case, because this is 0 and this is 0, so the Gauss law only, sorry, the Gauss surface only inside the plate between them, okay? So the Gauss law only EA Q enclosed over epsilon 0. This is sigma A over epsilon 0. So we get this one. Okay?
Yes, sir. Thank you. I understand.
Yeah. Because the charge move, for example, in the positive plate, the charge move to the right hand side. So we have only inside the region between the plate. And also in the minus charges plate, in the minus charge plate, the right hand side charge move to the left. Okay, so all of them only inside this one in the region 2, in the second region. Okay, anything? Any question? Okay, what about the potential difference? Potential difference, voltage or difference or potential difference. This one also potential difference means, okay, the potential difference is equal to minus A, let's say x dx 0 to d. Okay, so this is E times d. So this one is equal to sigma d over epsilon 0, and this is equal to sorry, this is d. So this is equal to q d over epsilon a. Okay. So if you use the definition of capacitance is equal to Q over delta V, then we get this is equal to epsilon 0 A over D. This is the capacitance for, well, parallel plate capacitor. This is capacitance for of parallel plate capacitor. So you see that the capacitance only depends on the geometry of the capacitor. Okay. What is the geometry? So for example, A is an area, area of the plate. D, distance between plate. Okay. This is the simplest thing. Any question? Any question?
No yet, sir.
Okay, clear, yeah? Okay, good. What about if the shape of the capacitor is cylinder? Cylindrical capacitor. So we have this interior conductor, and this is the exterior. So I think it's difficult to so let's say this one and this one. Okay. So this is the radius is, let's say, R1, and this radius here R2, for example. What is the capacitance of this one? Sorry, Q over so you know what is the potential in this case? Delta V. The potential for road, for example, the potential for road, let's say this is R here. The length is L, where R is very, very small, smaller, much smaller than L. Okay. And this potential will be lambda over 2 pi epsilon log R over R0 ya. Just a moment. Is it the opposite? Is it the opposite? Can you check whether this is R0 over R or R over R0? The A, let's say A is lambda over 2 pi epsilon 0 R, okay? So V is minus integral A lambda, sorry. Let's say for some R to the R0. So this should be lambda over 2 pi epsilon 0 log R over minus R over R0. Oh, okay. Okay, this is the correct one. So this should be Q over 2 pi epsilon 0 L log R over R0. Okay? Okay, so if we replace this, which one? Sorry, this is R2, yeah. Sorry, not R1. R2, sorry. So R2 is greater than R1. Okay? So it should be, in this case, so this should be Q over 2 pi epsilon 0 L log R2 over R1. Okay? If you use this definition, Q over delta V, it should be equal to 2 pi epsilon 0 L over log R2 over R1. Okay? Any question? So this is for a cylindrical capacitor. What about for spherical capacitor? Spherical capacitor. Spherical capacitor. So we have a sphere and then interior sphere and also the exterior sphere. Okay, so this is, let's say, R2 and this is, sorry, R2, this is R1. Okay. What is the potential difference between this one? So here in this space, the space between the interior space and the exterior space, the shell, interior shell sphere. So do you know? So this should be Q over 4 pi epsilon 0. This should be 1 over R1 minus R2. Okay. I should put Q over 4 pi epsilon 0. This is R1 times R2 over, sorry. It should be R2 minus R1 over R1 times R2. Okay. So the capacitance of the spherical capacitor is Q over delta V. This should be 4 pi epsilon 0 R1 times R2 over R2 minus R1. Any questions? So I will summarize in bahasa, okay, for the last 5 minutes. So hari ini kita bahas tentang kapasitor, terutama bahan dulu ya, terkait dengan bahan, sifat kelistrikan bahan ya istilahnya gitu. Jadi untuk kasus kita ini pada level Anda, itu kita cuma dikenalkan pada konduktor dengan isolator. Jadi konduktor itu adalah bahan yang baik untuk mengantarkan arus listrik, sedangkan insulator itu jelek lah ya untuk pengantar listrik. Sebenarnya penyebabnya ini karena konduktor itu secara mikroskopik itu punya yang disebut namanya nearly free electron. Jadi elektron semi bebas kalau bahasa Indonesianya. Jadi nearly free electron ini itu dia istilahnya dapat berpindah dari satu atom ke atom lain, sehingga makanya dia bisa merambatkan arus listrik gitu ya, bisa yang merambatkan arus listrik gitu. Jadi itu sifat konduktor. Nah, kalau secara kelistrikan, jadi kalau saya kasih dia muatan listrik, ya misalkan plus Q gitu pada misalkan bola padat dari logam gitu ya, karena dia itu konduktor. Jadi biasanya kalau dia itu metal atau katakanlah logam, bolanya ya konduktor itu nanti muatannya itu akan terdistribusi hanya pada permukaannya saja, permukaan luar dalam hal ini. Ya. Apa namanya outside area gitu ya, area apa outer area ya, area yang luar ya. Area yang terluar gitu. Jadi di permukaan luarnya saja, di permukaan dalamnya dia itu 0, makanya medan listriknya 0. Oke. Sedangkan isolator kalau saya beri muatan itu dia biasanya terdistribusi merata di seluruh volume. Oke. Nah, untuk elektrostatik yang ini untuk kasus kita, kalau untuk rapat muatan bebasnya itu adalah Q per volume dari bolanya. Jadi ini dianggap efek dari rapat muatan induksi itu diabaikan ya, omitted atau neglected itu diabaikan gitu. Jadi kita cukup punya ini saja gitu. Biasanya nanti kalau di studi isolator ada elektrostatik, nah biasanya itu muatan induksinya diabaikan. Taunya bagaimana? Nah taunya bagaimana bahwa itu diabaikan atau tidak? Nah biasanya kalau tidak dikasih tahu rapat muatan induksinya, berarti itu diabaikan. Jadi dianggap sangat kecil muatan induksinya pada isolator tersebut. Jadi yang dominan itu adalah muatan bebasnya. Oke, nah itu sifat kelistrikan dari bahan yang kemarin perlu dilengkapi. Kemudian kita membahas bab baru tentang kapasitor. Jadi kapasitor itu adalah sebuah alat yang dapat menyimpan muatan. Jadi kata kuncinya itu adalah menyimpan. Jadi menyimpan itu adalah disebutnya namanya kapasitansi. Kapasitansi itu adalah kemampuan kapasitor untuk menyimpan muatan. Nah, definisinya kapasitansi itu adalah ini, C dibagi Q total dibagi delta V. Delta V itu adalah beda potensial ya, potential difference atau voltage difference, sama aja. Q itu charge. Oh ya, saya lupa, satuannya, unitsnya ini, units dari satuan dari atau units ya. In English ya, kita in English, units ya. Itu dia farad atau Faraday. Farad ya. Dari kata Faraday, ditulisnya F kecil, kalau disingkat F besar, farad gitu ya. Satuannya itu. Nah, ini jadi saya ambil contoh nih untuk yang plat itu apa ya disebutnya plat itu. Plat sangat besar gitu bentuknya segi 4 gitu ya. Nah, dia kan E-nya tuh konstan. Jadi kalau itu terbuat dari konduktor, jadi plat ini dia akan terdistribusi di sisi sebelah kiri dengan kanannya. Gitu. Atas bawahnya tidak, karena dia kan sangat besar. Jadi dianggap itu ini tidak diabaikan lah ya, tidak ada gitu ya. Jadi makanya ini dapatnya tadi E-nya sama dengan sigma dibagi 2 epsilon 0. Nah, sedangkan kalau saya pasangkan nanti antara sigma plus dengan minus sigma, jadi antara muatan yang negatif dengan positif, itu jadi bentuknya seperti ini. Jadi di daerah 1 dan 3, E-nya tuh 0, yang ada cuma di bagian 2-nya saja. Kenapa demikian? Ya karena tadi, jadi muatan itu karena terbuat dari logam gitu ya. Jadi dia hanya terdistribusi merata di permukaan dalamnya saja gitu. Jadi ini istilahnya ya dia berpindah gitu. Jadi yang di sini kan tidak ada. Jadi dia berpindah ke sini. Gitu. Nah, jadi karena dia itu skema jadi seperti ini, jadi nanti bagian E-nya itu tidak lagi ada per 2, tapi sigma dibagi epsilon 0. Oke. Nah, delta V-nya, nah jadi gini, delta V gini. Kalau namanya delta V itu biasanya akhir dikurangi awal. Ya. Jadi akhir dikurangi awalnya itu dia negatif. Nah, karena kan di sini ada negatif, jadi nanti ini sambil dikalikan aja, jadi diambil mutlaknya gitu ya. Yang delta V ini ya magnitudenya saja delta V ini. Jadi ini adalah E kali D, ini adalah sigma D dibagi epsilon 0. Oke, didapat seperti ini, QD per epsilon 0 kali A. Dari definisi kapasitansi ini saya dapatkan seperti ini, bahwa C ini adalah Q dibagi delta V sama dengan epsilon 0 kali A besar dibagi D. Oke, nah kalau kita lihat di sini, kapasitansi dari sebuah kapasitor itu hanya bergantung pada bentuk geometri dari bendanya, dari kapasitornya. Ya. Dalam hal ini misalkan besaran-besaran geometrinya itu adalah A, luas permukaan dari pelat dengan D gitu ya. D itu jarak antar pelatnya. Oke. Nah, ini contoh lain misalkan yang kapasitor silinder ya. Yang kita kenal, kan sering kita lihat itu ada kapasitor bentuknya silinder, pelat juga udah ada kan ya. Nah, kalau kapasitor silinder itu mulai dari definisi potensialnya itu kita dapatkan untuk kapasitansinya C-nya seperti ini. Kemudian untuk yang bola, sphere, ya, kita mulai dari potensialnya, beda potensialnya adalah seperti ini, Q dibagi 4Pi epsilon 0, R2 kurang R1 dibagi R1 kali R2. Ini didapatkan bahwa C-nya itu adalah 4Pi epsilon 0, R1 kali R2 per R2 kurangi R1. Nah, kalau kita lihat, yang bagian atasnya ini, ya, yang ini, itu luas kan ya, R1 kali R2, satuannya luas ya kan. Sedangkan yang R2 kurang R1 itu satuannya panjang, dalam artian dia jarak antar bola dalam dengan bola luar gitu. Interior sphere dengan exterior sphere gitu ya. Seperti itu. Oke, itu sementara dari saya. Saya pikir cukup ya.